And I
Hello,
will start with
everyone.
sharing my screen. People keep coming in, that's perfect.
Yeah,
Good. In order to leave as much time as possible to our guest, I will start right now, and people can keep coming in during that time. So I want to welcome all of you. Thank you for this special initiative of the EleTher GIP. So my name is Jean-Charles de Hemptinne. I'm from IFPEN. And I first want to say a few words about our project, our joint industry project that you see here on this slide. It wants to be, as you see here, an industrial community on electrolyte thermodynamics. And we at IFP Energie Nouvelle, we are very much concerned about collaboration between different type of industrial partners, and more specifically between the users of the thermal and the ones that are responsible of making them available, that means the software vendors. Okay, so you see here the partners that we have, the user community partners and the software community. And amongst the software community, we have here with us in particular Dr. Shu Wang from AspenTech, who will introduce our speaker in a few minutes. And we also have Edouard Moine, who turned off his camera, but he's still with us. And he will chair the Q&A session. So regarding the Q&A session that we will have next, I invite you to write your comments in the chat, so as to make it easier for questions. Okay. So why is it that we're working on electrolyte thermodynamics? Well, the reason is that it is well, a very ubiquitous coming up in many different industrial applications. As you see here, this is just a non-exhaustive list: the transformation of biomass, battery, capture of CO2, geothermal context, and so on. And in practice, there are quite a number of challenges that come up with these thermodynamic applications. And if I can summarize them in three big items, it is the problem of the fact that these systems are often reactive. So that means that we need to have equilibrium constant. We need to have both chemical and physical equilibrium. The second item is that it's generally strongly non-ideal. And the third item is that we may encounter many different phases. So we need a very robust algorithm. So the combination of these three challenges makes this topic, I believe, quite something that we need to work on as a community. And the aim of this joint industry project, I put three items, threefold. The first aim is to identify as good as possible what are the challenges that applications are faced with. And if I summarize, I believe there are three ways to look at it, or ways of the difference between chemical potentials. One is looking at the solvents, or at least the neutral molecules, how the impact of salt is modifying the behavior of the VLE, which is generally called the sorting in or sorting out. The second impact is related to the ions themselves, or the reacting species, how they behave when they are in a mixed solvent compared to pure water. And this is the same property, in fact, it gives energy of transfer, is the same property that is also driving the liquid-liquid equilibrium. And the third challenge is the high concentration problem. That means when we reach the solubility limit, so the computation of solid liquid equilibrium. And this is without mentioning, of course, other issues, which are thermal issues, enthalpy and CP of these reactive systems, which is, of course, also very, very complex. So this is the first aim. The second aim is to then propose a workflow of best practices. I think there's nothing really exceptional about that, but nevertheless, it's worth looking at the need for data. If you want an industrial model, you need to be able to collect data, and data are generally not sufficiently available or may be inconsistent, and all of this needs to be evaluated. The second step is extrapolating, I would say, these data towards the process conditions. And the third step is then to correlate in an industrial process simulator. So using some kind of a existing thermal model that generally needs to be correlated. There may be many parameters to be identified, and that's a challenge in itself. The first aim of the GIP is collaboration, is promoting collaboration. This we have done in the past by within the working party already, the European Working Party. We have written this paper that I invite you to have a look at, which is where we promoted the use of applied thermodynamics as a key enabling technology for several sustainable development goals. And electrolytes are selected as a family of systems that requires particular focus concerning, because of the underlying physics that is often not well understood. And what we've done within the GIP in that objective is defining some case studies that is both simple and complex. I mean, as simple as possible to do real science, say, to really analyze the impact of different physical-chemical properties of the system, but sufficiently complex to really be able to answer industrial challenges. So here we have selected water, of course, always with an acid and a base, and a co-solvent, which then creates a system with, in fact, 9 components possibly, which is the ion and the ion pairing, which is a salt in itself. And the objectives of this GIP, of course, is to communicate, and this is what we are here for. We have created this webinar in order for you to be able to share the advances of academic developments in this field. So we have we have invited a known person in that field, and I let Chau now introduce him.
Thank you.
Sure.
Thank you. Yeah. Thank you, Professor Jean-Paul. Thank you for all the introductions here. My name is Shu Wang. I'm from AspenTech, and we are part of the EleTher consortium, and we are very glad to be here and contribute. Now it is my great honor to introduce you today's speaker, Dr. Chau-Chyun Chen. He is a Horn Distinguished Professor at Texas Tech University and the Jack Maddox Distinguished Chair in Sustainable Energy at the College of Engineering. He's a co-founder of AspenTech. He is the inventor of Aspen process simulation software for electrolyte systems, polymerization process, and small molecule drug solubility, CO2 capture with chemical absorption, and molecular characterization for petroleum assays. He joined Texas Tech University in 2013 to further research in adsorption thermodynamics, electrolyte thermodynamics, membrane separation, and others. He holds over 160 scientific publications and book chapters, and over 20 US and international patents. Dr. Chen received his bachelor degree in chemistry from National Taiwan University, and master's and PhD degrees in chemical engineering from the Massachusetts Institute of Technology. He is a fellow of American Institute of Chemical Engineers, American Association for the Advanced of Science and U.S. National Academy of Engineering. Now, without further ado, I introduce you Dr. Chau-Chyun Chen. Over to you, Dr. Chau-Chyun.
So, Dr. Bellini does not have a way to receive.
Is there a, can we mute?
Oh, okay, I didn't know that. I thought anybody can send or receive.
Can you see my screen?
Yes.
Yes. Yes.
Perfect. Thank you.
Okay. Let me see how I can move the slide. Okay, you can see my, okay, the slide is moving.
Yes,
okay,
perfect.
fine.
It's perfect.
Okay.
Thank you.
Well, let me
Please go
first say thank you everyone for giving me the time to share with you my work on electrolyte thermodynamics. And let me first give you the summary of my talk. I want to emphasize that rigorous and predictive thermodynamic models for multi-component mixtures are the key to first principle process simulation technology for simulation design and optimization. This may sound obvious, but I want to emphasize that predictive capability. We not only correlate data, but we actually rely on the models to predict the behavior of the solution, for all the components in the multiple component mixtures. And we never have enough data to correlate and develop the model and identify the model parameters. So ultimately, a successful model not only allows to correlate the data, but also, most importantly, to predict beyond the data probability. Of course, we know over the past century, we have seen series of thermodynamic models have been formulated, and they try to capture the physics of the electrolyte solution. And it is the physics, if we capture that physics, then we have a chance to do prediction reliably. Personally, after more than 40 years now, okay, of good learning and practice first at IFPEN Tech with all the customers there, and also now at TTU with my students. Personally, I feel the association electrolyte NRTL model has a real potential to fully support accurate correlations and predictions for multi-component electrolyte systems. So that's my conclusion. And let me get into details of why I say that. Of course, we all practice process simulation. As Charles was mentioned, that we use simulation to deal with electrolyte solutions. We cover CO2 capture, produce water desalination, lake brine mining, waste stream treatments, chemical production, cooling systems, etc. When we perform simulation there, they rely on the thermodynamic models to provide the properties that we need for the calculation in process simulation, whether it's distillation, whether it's absorption or reaction. And all these different thermodynamic properties, of course, are dependent on the results of the electrolyte thermodynamic models that we've seen in the literature. And there are many of them, including activity coefficient models and equation of state. Today, I'll focus on activity coefficient models because that's my my focus in my research here. Again, all these models allow us to, based on model parameters, predict the behaviors, thermodynamic behaviors of the solution at given temperature, pressure, and X. X, again, I want to emphasize that for multi-component solutions. And all these models, of course, depends on the data. I want to emphasize not only mean ionic activity coefficient, osmotic coefficient, vapor pressure, but it's also very important to consider excess enthalpy. Because again, coming back to process simulation, not only we rely on the model to predict, for example, CO2 solubility in the amine solution here as function of the CO2 loading, okay? But at the same time, we rely on the model to tell us what are the heat absorption when CO2 is absorbed into it. Only when we have these two accurately captured by the model that we can perform rigorous simulation for CO2 capture unit. So based on my learnings, I feel that the key characteristics of a successful electrolyte models, these models should formulate it with validated and consistent physical concept. And they should be rigorous and thermodynamically consistent. And they should use this number of adjustable parameters, and they should have physical significance. Talking about this, I want to mention the reason PISA model could not be used in process simulation is because it has too many adjustable parameters. And given that you cannot identify those parameters in a unique way to allow for robust prediction for mixtures. The model parameters should the dream of it is to use unary model parameters, i.e. Species specific. But very often we know we don't achieve that yet. And most models rely on binary induction parameters, and they are acceptable. And like the PISA model, it requires ternary parameters, and they are detrimental to process simulation. The model should provide accurate correlations of single electrolyte solution properties, all of them, whether it's activity coefficient or excess enthalpy. They should allow for robust, reliable prediction for mixed electrolyte solutions. Ideally, from single electrolyte solutions, they should be at least give reasonable prediction for the mixed electrolyte solutions. And they should also be available in process simulators to support industrial applications. So over the past almost 100 years, more than 100 years now, that we know all started with the Debye-Huckel equation. And with this, the Debye-Huckel equation, it captured the Coulombic potential for ion-ion interaction. However, without considering the other physical phenomena such as molecular ion interaction and so on, the model is only applicable to very dilute electrolyte solutions. For example, for sodium chloride, the mean ionic activity coefficient of it, Debye-Huckel could only represent very dilute region here. PISA did the major advancement in electrolyte thermodynamics in terms of industrial applications. It's a major improvement over Debye-Huckel because in addition to Debye-Huckel, the model introduced a virial expansion expression to describe the various two-body ion-ion and three-body ion-ion-ion short-range interactions. The model succeeded in accurate correlation of data up to 6 molar concentration, but the model would diverge at higher concentrations. Again, coming back to the mean ionic activity coefficients for sodium chloride, you can see that the PISA model correlated up to the saturation quite well, up to 6 molar. Okay. I mentioned one issue is that it requires three-body inductions here, and therefore ternary parameters. And in process simulation, it's very difficult to identify them and also to implement in simulator. A major drawback of the PISA model is its temperature dependency. Because of virial expansion coefficient parameters, their temperature dependency is unknown. I want to also emphasize that with PISA model, at higher concentration, it diverges. Okay, again, for sodium chloride, it represents the data well up to 6 molar, but then after that, it diverges. And of course, when we deal with 6 molar or deal with 10 molar or 100 molar electrolyte solution, the gamma from PISA model will be extremely unreasonable. So with that in mind, back in '82, I developed the electrolyte NRTL model. Again, we built on the work of Peter. We used the Peter Debye-Harkel expression that he developed, but we replaced the short-range interactions with local composition model. The local composition model actually is consistent with the Debye-Harkel expression, and because of Debye-Harkel expression, we consider so-called local electron neutrality and like-ion repulsion when we derive the local composition expression using the NRTL model. The model actually works well for many electrolytes with concentration up to salt saturation, even to 100% salt. But the model does not work well for ions exhibiting strong associations such as lithium ion. And looking at the sodium chloride again, the NRTL is shown in green line here. It captured the data up to 6 molar. Beyond that, it deviates. Again, that's because sodium ion also exhibit association behavior. Today, in IFPEN and in many other simulators, NRTL has been introduced, and it has brought a lot of successes, especially for CO2 capture and the brine solution desalination processes, but also many failures. For example, for lithium chloride, given the mean ionic activity coefficient data, NRTL represented well up to 6 here, but beyond that, the data will never be captured by NRTL. Again, I want to emphasize that the two key concepts in NRTL, so-called local electron neutrality and like-ion repulsion, actually followed the view on electron on cloud from the Debye-Harkel limiting law. With this two hypotheses, if we look at it with molecule in the center, then the ionic concentration around the central water molecule should satisfy electron neutrality, while around the center cation or center anion, only ions of opposite sign can be present. As I mentioned, the model has been extensively used, and recently at TCU, we developed the first and only validated electrolyte thermodynamic model for high salinity produced water. And being in Texas, this is a major issue for Texans. We generate a lot of oil, but when we generate 1 barrel of oil, actually we generate maybe up to 5 barrels of dirty water, the produced water. So the model covers sodium, potassium, magnesium, calcium, strontium, barium, chloride, sulfate, bicarbonate, and carbonate, with temperature up to 200 degrees C and concentration up to saturation. It covers all the thermodynamic properties and calorimetric properties and salt solubility. And the model has been used in many research groups right now to develop novel processes to treat water and to recover the trace metal ions. And down here, I just simply show that not only we capture the mean ionic activity coefficient in general, but also to a large extent the salt solubility for multi-component systems of different salt. And this one is the phase diagram generated for the system with 3 cations and 2 anions. Also, the model has been used to correlate the CO2 solubility in different solutions that may be present in produced waters, not only for single and mixed, binary electrolyte solutions, but also for the for produced waters from different wells. Well, the model, we claim success on it. The model still has its issues. For example, calcium chloride solution, the model actually could not capture very well the real pressure data. And low concentration, it is fine, but high concentration, it does not. And on the right, I show the mean electric coefficient. The solid lines are the NRTL correlation, while the dashed lines are the data, the pseudo data, simulated data from the PISA model. So you can see that NRTL still could not capture the trend well at high concentration. So we've been looking into it. Why that's the case? What do we miss in the model? And we do know that the ions in the solution, actually they could form so-called double solvent separated ions to SIP, where the cation and anion are separated by solvent shells. Or could be solvent shared ion pair, where the two ions are separated by only one water molecule, or they can form ion pairs. And all these species are results of association. And in aqueous electrolyte solutions, we know we have water-water self-association because water can be electron donor and electron acceptor. And we see water cation cross association that results in cation hydration because cation is electron acceptor. And water anion can also cross associate, again forming anion hydration because anion is electron donor. And also cation anion will cross associate and they form ion pairs. And that's the phenomenon I think we missed in NRTL. And the question is, how do we capture all these different species present in solution? I want to note that when we consider association, we need to make sure the association term is compatible with Debye-Huckel and also with the local composition model. And indeed, all these associated species, they follow local electroneutrality and lack ion repulsion. So a few years ago, one of my postdocs, he looked into this association behavior, and he developed the model to capture the association. And he found that the model can actually represent, correlate the data very accurately until saturation for all the electrolytes, 46 electrolytes he examined. Looking at this one, with the association model, you see the black line here, indeed it captured the data. So for us, for this model, our priorities now is to examine its predictive capability, expand the scope of the electrolytes from 46 to 135 that we have data for. And also we need to apply this model to show that indeed it solves industrial problems that we could not address with NRTL. And lastly, we need to convince AspenTech to introduce the model into Aspen Plus. So again, back then with sodium chloride, NRTL fails at high concentration, but with association model, it now represents the data. And for lithium chloride, NRTL could only represent up to 6 molar again, but with association model, it captured it all. So this slide summarizes how we formulated the association model. Of course, we took advantage of the work by the Dr. Stan Sandler's group that he actually initiated this work back 20 years ago. Okay, almost 30 years ago, my God. Interesting. So the association term could capture contribution from association of the electron acceptor, electron donor, and also for the solution of other species as well. What I want to say is that the bounded site fraction, the unbounded site fraction, the way we formulated it, we simplified and used the chemical theory to derive the expression. And this chemical theory actually is consistent with the Laminar isosome or extended laminar isosome for multi-component adsorption equilibria. And of course, we need to know the equilibrium constants from data. And this equilibrium constants, we express it with a reference to the self-association of water. And we try to bring ion-specific parameters and identify for the cation, for the cation and anion, or the acceptor and donor, identify the ion-specific parameters with this formulation. This, of course, is empirical, and we need to test how well it represents the data. So we tested for over 46 single electrolyte solutions at room temperature, and we focused on mean electric coefficient up to source saturation. The fitted parameters include the association parameters, the ion association strengths for acceptors and donors. And of course, we still have the NRTL term there, and therefore the tau ij's for the NRTL parameter. So that means for single electrolytes, we have 3 parameters, 2 source-specific parameters, and 1 ion-specific parameter for each ion. With that, we found that indeed, association NRTL model provides major improvement over NRTL. For many of the electrolytes, such as potassium and cesium and so on, with different anions, NRTL works very well without a problem, and so is association NRTL model. But for many of the strong associating ions, electrolytes made up of those strong associating ions, NRTL fails, and with very high standard deviation, Loomis square error, with respect to mean activity coefficient. But those high errors, such as lithium chloride or lithium bromide, would not be addressed with the association model. Here are the figures that we show how the various mean activity coefficient of the 46 electrolytes are captured. For 1 electrolytes here with same cations. Okay. For example, here we have lithium bromide, lithium chloride, lithium nitrate, and lithium sulfate, and lithium iodide, and they all can be captured very well. Next, for 1 electrolytes with same anion, for example, with the bromine anion, we replace the cations. Again, the model captured all the different 1 electrolytes very well. It works not only for 1 electrolytes, but also for 2 electrolytes, such as magnesium, calcium. Now, remember, with NRTL, we could not represent calcium chloride, but now we can represent it very well. And the next slide shows the 2 electrolyte mean activity coefficient representation for 2 electrolytes with same anions. Again, they are all well captured. Looking at the model parameters, of course, the high interest to us is the association strengths of the various ions. And we see that the association strengths of ions actually follow the ion size. The larger they are, the weaker the association strengths. For example, lithium is the smallest one, and it has the highest association strengths. And sodium is larger, therefore it's coming down. Another fact we found is that, of course, with double charged ones, they showed even stronger association strengths. And keep in mind, we did use water self-association as a reference. So when association strengths of ion goes beyond unity, then they are so-called structure-making ions. When they become less than unity, they are structure-breaking ions. And indeed, all these trends can also be captured, can also be in a way represented in the aqueous electrolyte density data. With density data, the structure-making ions, with presence of structure-making ions, the density goes up when these ions are introduced, while the structure-breaking ions, when these ions are introduced, the density of the solution will go down. Looking at details of the representation of the gamma expression, we show that for lithium chloride, this is a highly associating system. And we see that data is shown in the black line. Of course, it represents data and its extrapolation. But among the three contributions, clearly association term represents the highest contribution. It's true not only for activity coefficient of lithium chloride, but also for activity coefficient of water as well. The water activity coefficient actually very close to the water activity coefficient as calculated from association term alone. Another very interesting observation is that if we look into the bounded side fraction of the ions, first, for example, use lithium chloride as let's focus on lithium chloride. That's the black line here. For lithium ion, it's strongly associating, right? When it is in infinite dilute solution, lithium ion is completely associated. The bounded side fraction of lithium ion is unity, and that means it's all hydrated. As you increase the lithium chloride concentration, the bounded side fraction of lithium drops, eventually go down to about 0.28. And at this point, there's no water present for pure lithium chloride electrolyte. And what that means is that this is the extent of ion pairing of lithium chloride. So you can see the transition from 4 hydrated ion into an ion pairing. Look at the anion, the corresponding anion for lithium chloride. Initially, chloride will form a small amount of ion pairing. As chloride doesn't hydrate, it has a very weak association strength, so it doesn't really hydrate, but it would form ion pair with lithium. And as the lithium chloride concentration goes up, then ion pairing goes up. Eventually, it's basically all paired with lithium ion. So let's look at what ion hydration means to us. So let's look at the chloride electrolytes with different cation, lithium, sodium, potassium, and rubidium, and also cesium. Of course, we know lithium has the highest ionic strength, and it shows the highest gamma value. Cesium has the weakest one because it's the larger species. It has the weakest, the lowest mean ionic activity coefficient. So that tells us that as hydration happens, no gamma goes up. While we look at the ion pairing, we know lithium bromide, let's deal with lithium ion here and changing the anions from bromide to nitrate. And nitrate has the strongest association strength that suggests that it will form ion pairing most strongly with lithium. And indeed, that's the case. As the association strength goes up, ion pairing increases, and gamma goes down. So ion pairing reduces gammas. So following that, let's look at the temperature effect. So lithium chloride solution, as the temperature goes up, we see that the association strength will go down, and therefore gamma of lithium chloride will go down. Same thing with HCl. As temperature goes up, hydration goes down, and gamma goes down. And these are the same plots, but for 2,1 electrolytes, magnesium chloride and calcium chloride, again, temperature goes up, gamma goes down. To check the validity of the model for mixtures, another way is to see whether it follows so-called Hemptinne's law. Hemptinne's law, of course, is an observation. It says that the logarithm of mean ionic electric coefficient of an electrolyte in a mixture of constant total molality is directly proportional to the molality of the other electrolytes. So what that says is that if you put HCl lithium chloride solution together and you maintain the constant molality and you increase HCl concentration, so initially it's all lithium chloride, down to here is all hydrogen chloride. Of course, these two endpoints are captured by the single electrolyte model of the parameters. So, but these two follows, again, calculated and determined by single electrolytes. The question is whether the model gives us a linear correlation or not. And it does. Another check for it is the trace activity coefficient for, in this case, HCl in another solution. For example, HCl in lithium chloride. And we increase lithium chloride concentration and we keep HCl concentration at the infinite dilution at trace concentration. And we see how the model will predict mean ionic activity coefficient HCl, and the model predicts them well. So coming back to the lithium chloride solution, now it represents now mean ionic activity coefficient and osmotic coefficient and so on. But for calculation, for the process simulation, we care about vapor pressure of water in lithium chloride solution. And here I show the comparison between NRTL model in dashed line and the association model. And for the first time, now we can represent vapor pressure of aqueous lithium chloride solution. And from that, of course, we can develop the solubility model. So we have checked into the more predictions. For example, water, lithium chloride, lithium nitrate vapor pressure, or even adding the lithium bromide and lithium iodide into it. And just based on prediction from the parameters determined only for single electrolytes, it shows that association model quite satisfactorily predicted the data. The model works not only for aqueous electrolytes, but also for non-aqueous electrolytes that methanol lithium chloride solution here. Again, here we show the vapor pressure of methanol as you add lithium chloride to it. And NRTL is not adequate, but association model allows us to capture the data. And also for mixed solvent ones, these are the predictions as well. NRTL results shown in dashed line, and the association model are shown in solid line. And here, this of course is constant pressure isobaric data. So we see the temperature variation with the methanol content. And as we vary lithium chloride concentration, the model predicted the phase diagram. And also, if we capture the activity coefficient right in mixed solvents, then we can use it to predict the salt solubility. In this case, this one actually is very interesting. Actually, it shows two types of salts. First, when water is abundant on this side, the salts precipitating are the lithium chloride hydrate, monohydrate. But as water is diluted, taken away, replaced with methanol, then you see lithium chloride and hydrous lithium chloride precipitates. And the association model can capture them very well, while NRTL model can only capture the trend, but not the data. Looking at the mean ionic coefficient of the sodium chloride in the mixed solvents, in water methanol mixed solvents, the model, again, as from association model, we show the solid lines that represent the data. NRTL was able to capture it to a large extent as well. But what's interesting is the temperature effect. This is 298, and then 308, and 318. And while temperature is changing, association model still capture them very well. One of the industrial systems I worked on when I was back at AspenTech was to develop caustic solution model for core alkaline industry. And with NRTL, for 40 years, I was never able to represent it well. But with the association model, we now have a successful model for caustic solution. And again, the model parameters are only the association strengths for the ions and the NRTL tau Ij parameters, and their temperature, and of course, their temperature dependency as well. And for the first time, I'm very excited to see that we represent not only the vapor pressure of caustic solution across the entire temperature range, but also the heat of solution represented with a Merkle plot. And given that, then the industry could really make use of it in process simulation. Jin Charles did ask me to look into equation of state for electrolytes. And this is not my focus of research, but I just want to show that the EPC SAPT and the ion pairing equation of state results. I want to make some maybe a superficial comment. From my perspective, the model still cannot represent the single electrolyte property. On this side, we see the mean ionic coefficient plot against concentration for various for cesium chloride, rubium chloride, potassium, sodium, and then for lithium chloride. And on the right-hand side, this is for the bromide salts. And well, it seems to be able to represent some electrolytes, but the key challenge for association model is lithium chloride. And lithium chloride is still not represented satisfactorily yet. Another issue with the EPPC SAPT is the temperature dependency. This one is the mean ionic coefficient of sodium chloride and sodium bromide as the temperature is changed, and clearly the temperature trend is completely lost. That means it will not be able to provide correctly the excess enthalpy or the heat of solution. I do appreciate the work on ion pairing equation of state, where the association term is now decomposed. It's being revisited, and I do agree that the problem with the current EPPC SAP equation of state is that the association term is not properly formulated yet. Of course, that's my personal bias. But with the ion pairing equation of state, it decomposes into three terms. I would argue that one model should be able to represent both ion hydration and ion pairing. Therefore, I would hesitate to consider breaking down the association term into ion term and ion solvation term and solvent term. There should be one model that represents all the association between ions and solvents, and ion and ion. With that, I want to conclude by sharing with you the next steps for association model. As I mentioned, we are in the process of determining model parameters for all single electrolyte solutions with sufficient data. And so far, we have identified about 130 of them. But equally important, we need to examine and validate prediction for mixed electrolyte systems. I have shown some initial successes, but no, we need to do a comprehensive examination for it. And then, of course, extend the model to mixed solvent. We have done some initial work, but with such a large scope of the work, we have not been really focusing on mixed solvent electrolyte system yet. Equally important, we would develop high precision models for electrolyte systems of industrial relevance. I mentioned caustic solution, that's one example, and there are many more to be done. And then we would want to have the model incorporated into process simulators, and then hopefully put together a textbook to explain the models and also to report the parameters, and hopefully also teach people how to use the models together with IFPEN. With that, I want to express my appreciation to all the collaborators and most importantly, my students. And of course, I've been at TTU for 11 years now, so I have graduated 18 PhD students. They are my pride at the TTU. With that, I thank you for your attention and happy to answer any questions.
So thank you to Professor Chen. I want to warmly thank you, Professor, on behalf of all the participants. I think it was a very nice presentation with a lot of information. So we have already many questions in the chat. So I will start with the question of Marie and Waria, who ask, what is NRTL accuracy for higher valence ions like Ln3+, An4+, etc.?
Let me come back to the okay. Let me come back to the Teams meeting and look at the chat. So
the first one.
Which one are you talking about? There are indeed many questions. I appreciate that.
Yes, I am talking about the first one. What is NRTL accuracy for higher valence ions?
I'm sorry, I don't understand your question. So yeah, if you can show me which one that we are talking about, from whom?
I don't know if Marie or Waria want to detail the question or.
Okay, yes, I see that.
Mean,
what's
in
the
your examples,
NRTL?
You showed only 1+ and 2+ cations.
Right.
So I was wondering, what is the accuracy of this model for higher valence cations, such as lanthanide or actinide?
Well, with NRTL, it's going to be worse because they are triple charge ones, right? Yes. And the ion size is not very different from other double charge ones. Yeah, we have used the association model to address the rare earth element ions. Yes.
Okay.
I did not show that in this work. And
what is the accuracy as compared as Pitzer, for instance, which is the most famous one, I guess?
For decoration purpose, okay, for lanthanide and so on, I would say they are equivalent because if you look at lithium chloride, look at the magnesium chloride, you see that we fit the data very well. And with rare earth elements, we have examined all 15 ions there, and the results are excellent.
Okay, good. Thank you.
Thank you. Another question from Vladimir, who asks, can you model sodium sulfite water solubility diagram with your model?
Is it sodium sulfate or sulfite?
Sulfate.
Sodium sulfate, yes. Yes, that for sodium sulfate, as I reported, we actually have a comprehensive model for produced water, including sodium ion there and also sulfate ion there, yes. And the phase diagram for it is actually captured with NRTL. And we expect to do better with association model as well.
Okay, thank you. Another question from Véronique Lachet, who asks, in case of water-methanol mixed solvent, do you use an association contribution for water-methanol interactions? I mean, is there also an association contribution for the binary mixture without the electrolyte in the mixture?
I didn't quite capture that. What's the, okay, in case of water methanol mixed solvent, do you expand association contribution? Yes, that's accounted for. Yes, of course. Yeah, water self-associate, methanol self-associate, and the water methanol cross-associate. They are all considered simultaneously together with the ion pairing and ion hydration for the electrolytes. They are all considered.
Okay, thank you. We have another question from the Dr. Martin Schiller, who asks, how many parameters does the association NRTL model need for an electrolyte water binary and an electrolyte solvent binary? And he also asks for the temperature dependent, the covered temperature dependency.
Okay. By the way, the chat, it's very, very helpful. I can see the exact questions being asked. Yeah, as I reported, they are the NRTL binary interaction parameters and ion-specific parameters. So at the room temperature, we have two parameters from NRTL and then one association parameter from each ion. So there'll be two of them, but they are ion-specific. So therefore, the parameter we identify for sodium in sodium chloride solution is the same as those in sodium sulfate solution. So that's question number one. For the temperature dependency, the model parameters are energy parameters. Therefore, the so-called Gibbs-Helmholtz expression would allow us to describe its temperature dependency. And with that, we typically use 2 or up to 3 parameters for temperature dependency.
Okay, thank you. I don't have if there is any comment. Everybody can speak and ask their questions. For the moment, we have another question from Susanna, who asks, what is expected schedule to incorporate the model into process simulators? I think NRTL with association, but I'm not sure.
Yeah, the NRTL, of course, is available in virtually all the simulators today. And the association model, the work was actually developed, sponsored by AICHE and AICHE Rapid Institution. And in that Rapid community, we have IFPEN, we have Chem Stations, and Aviva, and also Siemens, all the PSE, and they are all aware of the work and they have access to the code. So the question is, I think ultimately it will be determined by the industry demand. The timing of implementation will be influenced by the industry needs.
Okay, right. We have also a question from Alia Basileva about sulfuric acid and water solutions. She remarked on your slide 17 that is not on your slide 17. She asked if you tried to modeling this mixture, sulfuric acid with water.
with sulfuric acid H2SO4.
Yes.
I gave a talk yesterday, and someone asked the same question. We apparently, when we did that work, that sulfuric acid mean activity coefficient was left out, so it's not included there. But we actually have modeled sulfuric acid solution all the way from pure water to pure sulfuric acid, actually to SO3 as well, when water is taken out, using NRTL model, and that was very successful. In a way, sulfuric acid solution is more like a single sulfuric acid dissociate into H plus and HSO4 minus. So it's more like a 1,1 electrolytes. So yes, sulfuric acid is not a problem. And for acetic acid, of course, is a weak electrolyte. And actually, we are preparing a paper to cover the pH data regression and also VOE regression with the association model for aqueous solution of acetic acid, lactic acid, and butyric acid and their mixtures. I'm hoping to have that submitted to fluid phase equilibrium this month or next month. And yeah, for acetic acid, the question there is not mean only activity coefficient, but rather efficacy or the vapor pressure of acetic acid in the solution.
Okay, thank you. Another question, does your association approach also cover weak solvents, or do we need to use a true chemical approach?
What do you mean by weak solvents?
It's a question from Jean-Charles. Maybe Jean-Charles.
Yes. Yes, I mean, weak solvents are sorry, not weak solvents, weak salts, I mean, weak salts. So salts that don't fully dissociate or that are known for forming ion pairs in a significant amount. So like carbonic.
Could you give me an example?
Yeah, like amines or like carbonic acid that are not fully dissociated.
Okay, so you're talking about weak acid, right?
Yes, I'm sorry, not solvents.
Okay, yeah. I mentioned earlier that we are actually preparing a paper for aqueous solution of acetic acid, butyric acid, and lactic acid. They are all weak acids. And of course, we do need to consider the chemical reactions because over there, the dissociation is real, right? It's a chemistry that you need to capture as solution chemistry. And as part of that, you consider the activity coefficient for the ions and also for the molecular species there. And we have been able to represent it very well with association model.
So you combine both association model and the chemical equilibrium.
Yeah, yes, of course. That's right. Yes, you need to do that.
Okay, thank you.
Jean-Charles, I propose that you can continue with your second question if you want.
I continue with my second question. Okay. Yes, my second question was related to the association in mixed solvents. That means we know that in non-aqueous solvents, the association will be orders of magnitudes larger than in aqueous, than in water. So I was wondering whether using parameters that don't take into account the solvents, as you do, it seems to me, how well does it describe this association or this ion pairing in water versus non-aqueous solvents?
I agree with you that the association in non-aqueous solvent could be very different from the association in aqueous solutions. I mentioned that we have not devote enough attention to mixed solvent electrolytes yet. We have done some initial work. By the way, we do have an association NRTL model developed for non-electrolytes before we introduce this association model for electrolyte solution. And we found that the association parameters identified, the solvent-specific association parameters identified for one data set could not be really used in another the binary system for the same solvent. So I think you are right about that, and that's something we all need to look into it. I have no answer for it.
Yeah, you can have a look at our latest paper.
Yeah,
we use
for aqueous electrolytes.
Bjerrum theory.
Yeah,
use the Bjerrum theory that, yes.
Sorry, for aqueous electrolytes, we may be lucky because that universe itself is give us a lot of opportunity to do research along in aqueous solutions. Okay.
I was saying that we use Bjerrum theory that takes into account the dielectric constant of a solvent in order to describe this association, and that seems to work. Well, not perfectly, but it goes in the right direction.
Okay. Yeah. That's one possible direction. I agree.
We have also a question from Weifan, who asked about your comments about the differences between your association term and the one included in the SAFT models.
Well, in the model we implemented is a simplified one, which we call it chemical theory, and I expressed that in the slide. Yeah, I'm trying to avoid the parameters that are based on the molecular simulations.
You can take directly the parameter, for example, from a PC-SAFT equation of state and put it in your association term, or absolutely not?
No, they are not compatible because, as I said, we simplified the expression.
Okay.
Yeah.
We have another question about your slide 22. So I don't know if you can come back to this slide.
Okay, I mean, I know the slide. So yeah, the ionic radii are bare ones, not hydrated ions. In the gas phase, salt or ion content considered in the gas phase. I don't understand the second question. Why is the gas phase salt? Why would salt go into gas phase? Dr. Yu, could you comment on that? What do you mean by your question?
Okay, thank you, Professor Chui. Thank you very much. My question is actually the salt it can present in the gas phase.
Salt can go into gas phase.
Yeah. In the real situation.
I do not think so, unless we're talking about very high temperature ones, but not in aqueous solution.
Okay. In your research, the gas phase is just is a pure solvents, no salt.
Right. Yeah, unless we are talking about weak electrolytes such as acetic acid or CO2. No, they don't dissociate completely. Therefore, they are molecular species present, molecular acetic acid rather than the acetate ion or proton ion. And the molecular acetic acid, yes, it has its vapor pressure. It will go into the vapor phase. But when it goes to vapor phase, it's the molecular species that goes to vapor phase.
Okay. Okay. Thank you. Thank you.
Thank you.
So thank you. I don't see other questions, Jean-Charles. I don't know if.
Yes. I think that that we need to thank our speaker again, very much so, and I'd like to thank all of the participants also, because this was a very an innovative type of discussion, and I believe it has been very well received, and the content was of great both scientific and industrial interest. So thank you, Professor Chen, for having come to us.
Yeah, I want to thank you and also thank everyone for giving me the 1 hour to share with you my work. Thank you very much.
Yes, and thank you to Dr. Wang, Shu Wang, who has suggested to invite you, and all the partnership that we have. So thanks to everybody, and hope to see you sometime in real life.
Yeah, thank you. Bye-bye.
Okay, bye.
Thank you.
Bye-bye
Thank
now.
you.
Thank you.
Thank you, Jean-Charles. Bye.
Yes, bye. Merci, Edouard. Merci. Yes, ça,